Hi there. This talk is on simulation of a cellular energy system, including hierarchies and neighborhoods. It is joint work of Gabriel Dengler, Peter Bazan and myself, and we are all from a computer science lab at the University of Erlangen in Germany. And this is the structure of the talk. First, I will give you some background about the framework i7 AnyEnergy, in which all of this has been implemented. Then I will present you the cellular approach in general, and then our actual contribution, which is managing energy in such a system. Then I will talk about computational complexity, show you a larger example for the evaluation, and finally give some conclusions. So let's start with i7 AnyEnergy. First of all, I would like to give you an impression what is possible with the tool. This is an animation of a simulation model, and in it we model every county of Germany as an energy cell, and we have about 400 of them, and for every such county we have the capacities of the renewable generation units, and also we have the demands. And then you can switch between different presentation modes for different scaling, and you can also look at the residual load, for instance, that is demand minus renewable generation in each county. And you can also just look at photovoltaic generation and so on. So here you see some features of i7 AnyEnergy. We have, of course, building blocks for the most important energy components like demand, load, PV, battery, heating, and so on. And it is multi-energy, meaning that we can have different energy carriers such as electricity, heat, hydrogen, and so on. And it is based on the so-called cellular approach, which you see on the right side. We have energy cells which can be aggregated to higher hierarchy levels, and we also have neighborhood relationships. More about that later. Then also we have interfaces for a flexible and efficient access throughout the complete model, and we also provide certain control strategies for such decentralized systems. And also the tool offers possibilities for easy drag and drop, for rapid visual modeling, and if you have a more complex model, you can configure it also with text files or a database. Finally, we have nice visualization facilities based on the underlying tool AnyLogic. And already many use cases have been done with i7 AnyEnergy. For instance, on the level of houses and neighborhoods, the most recent model is a Carnot battery for renewable energy. Also on the regional and national level, the most recent model is sector coupling of electricity, gas, heat and mobility in Bayreuth, as you can see here, and also mobility related. So for instance, we have provided a model for the charging of electric buses in the city of Nuremberg. Let's now move to the cellular approach. The general concept is already known at different places. So for instance, it has been suggested by the German Association for Electrical and Electronic and Information Technologies, also known as VDE, and also has been researched in certain German projects like, for instance, C-cells. Also, the idea is around under different names. So for instance, local energy management, energy communities, energy hubs, peer-to-peer energy trading, or also fractal structured energy systems. However, very often only the concept and the architecture of such a system is described, but not yet control strategies and algorithms for it. And we have found mainly these three papers in which that is also been discussed. And either they are on hierarchies or they are on structures in which we have neighborhoods. But no one has considered the two in combination. So therefore we think this is a contribution of this paper. So the basic idea of the cellular approach is that you have cells with which you structure the overall energy system. We can start with atomic energy cells, like shown here, for instance for the demand, for the generation, or for the storage, and they all need a cell controller. And they can be combined to an aggregated energy cell, like here, which aggregates such basic atomic energy cells, but it is also possible, of course, to aggregate already aggregated energy cells. And in such an aggregated energy cell, you have two kinds of controllers. First, a hierarchical controller, which controls the subordinated energy cells, and it is also possible to have neighborhood relationships, and therefore you also need a local controller which can control the energy flows with the neighbors. Overall, a topology is constructed like this, in which you have the atomic energy cells aggregated to aggregated energy cells, aggregated again to higher level aggregated energy cells, and also you can have neighborhood relationships between them. And in order to control the overall system, you of course need suitable control strategies. And such control strategies are the main contribution of this paper. Let us first look at the perspective of a single energy cell, as shown here. It can have energy exchange, which we call energy flows, with lower level energy cells, as here, with neighbor energy cells, and also with energy cells on higher levels. And for all of them, we need suitable controllers. And it is important that we can now set control strategies for managing these energy flows, and they can actually be set arbitrarily. You can program your own control strategies. Here we present one which tries to do local load compensation on all levels of the cellular energy system. So it tries to do a self-consumption on the current level if possible. If not possible, a compensation of the additional demand or excess by batteries, just by charging and discharging them. And if it is not possible to get a balance, the remaining balance must then be resolved via neighbor and higher level energy cells. And that is not just done on one level, that is done recursively over all levels. And in the end, that leads to the control of charging and discharging of all batteries in the system, if we don't have controllable loads. And here is a little example to explain that control strategy. You see three atomic energy cells, which are aggregated to one hierarchical energy cell with its hierarchical controller. And the procedure starts by calling a function calc z from that hierarchical controller. It recursively calls all children energy cells and does this call of calc z. In order to get the initial power balance, it wants to get the actual flow without any external request. Like for instance, it asks the consumer how much it would like to consume. It says 3 kilowatts and gives that back as a function result. Then it goes to the next energy cell, the producer, again with a call of calc z, and gets as an answer 4 kilowatts production. And then it asks the battery as well and gets as an answer 0 kilowatts at the moment. So a balance would now be 1 kilowatt needs to be exported. But the aim of the strategy is to get a local balance and not to export anything to the higher level. So therefore we do a second function call called calc f, which again goes through the atomic cells and asks them for different energy flows. So it starts with a first cell, the consumer, and asks if it could consume 4 kilowatts, but the consumer says, no, that's not possible. So then it goes on with the producer and whether it could produce a little bit less, but that's also not possible at the moment. So then it asks finally the storage, the battery, and asks it to charge 1 kilowatt, and that is possible, and that is the function value, which is the answer, and that allows for that hierarchical controller to set the balance to 0 kilowatts, and we have resolved the balance locally. So that behavior can be accomplished with two recursive functions, calc_z and calc_f, which can be applied on the complete topology. So first of all, calc_z is called, for instance here, from a higher level EC energy cell. The call z function of a certain energy cell is called, and it is recursive, so therefore it calls all the children energy cells also with calc_z, and it gets the initial power flows, that is the actual power flows which would happen if no request would be set from the outside. So then here we just see one such children energy cell, but normally we would have more than one. After all these calc_z calls, we can compute the balance and call calc_f, and that is shown here. Calc_f gets the energy flows which have been gathered by the lower level energy cells by the calc_z function answer. It computes the power balance on that level, and if it is non-zero, which is probably normally the case, so then it can compute some other requests for the lower level ECs and communicate that with calc_f. So for every lower level EC, it sets new requests for them according to some strategy. For instance, just to ask the children in a greedy manner to resolve the balance. Others, of course, would be possible. And then this calc_f is called for every children, as we see here. We see it for one children here, but normally for one child, but normally it would be for several ones. It gets new energy flows then from these children and can adjust the own power balance and can compute the own energy flow, which must be provided to the higher level in that answer. And then here on that level, also it is embedded in a calc_z function, and after that a new calc_f happens such that everything is applied recursively on all levels of the topology. So this can now be generalized to also neighborhood relationships, as you see here. Our energy cell in the middle has now also a neighbor, and the procedure is as follows. The higher level energy cell calls the energy cell, and this first the control is given to the local controller. That first gives over to the hierarchical controller, which asks the children about the energy flows and tries to resolve the balance. And if that is not possible, then control is given back to the local controller, which asks then the neighbors to do that. Control is given back, and then again back to the higher level energy cell. So this is only the principle. Of course, time is not enough to explain that in detail, but if you look in the paper, you see algorithms which explain that on an operational level. Also in the paper, you find expressions for the computational complexity. We have found that the complexity is still polynomial, which is good. Of course, for the purely hierarchical case, it is better than for the case also with neighborhoods. And also we have looked at examples, a larger example which has been generated randomly. Here you see its parameters. In the case of both neighborhoods and hierarchies, less power must be transmitted over the hierarchical controllers. Coming to the conclusions, I would like to say that i7 AnyEnergy is a multi-energy simulation tool based on the cellular approach, and it is rapid for rapid modeling, scalable for larger models, has visual modeling facilities but also textual. We have We have done many use cases with it, and it is currently in preparation for open source. So then the cellular approach combines hierarchical structures and neighborhoods, for which we have local and hierarchical controllers, and we also can provide adaptable control strategies. And here we have investigated in more detail one which does local load compensation on all levels in a recursive manner. And further work is, of course, possible in many directions. For instance, other heuristic control strategies, also in combination with LP and MIP solvers, more sophisticated building blocks, for instance, batteries with nonlinear effects, and also performance improvements of this approach. Thank you very much for your attention.